It should be recording now. Hello, everyone. Thank you for coming to today's event. It's the first event of the Digital Health Week for AIM. And today we're just going to go over a little introduction for the Datathon that we'll be running this week and a brief tutorial on how to begin a Datathon. So just before we start, there's a couple things that I wanted to cover about the Datathon. So the Datathon will be on this heart disease data set that was that's online and available on Kaggle or on the Google Drive link that I can post after the event. And basically what we really want, so this is like an educational event, so what we really want is people to just learn how to deal with data and how to explore a data set. So we're just going to basically open it up and get you to figure out anything interesting in the data set and anything you find anything in the data set that you find interesting, and basically do like a mini write-up, maximum 1 page of whatever you found, and also and just submitting that at the end of the week. And also just any data analysis that you've done, you can also submit with it. But basically what we really want is an explanation for what you found rather than just like just the analysis itself. So yeah, so, and the other thing is the price for the event. So we will, at the end of the week, after we get the submissions, we'll look through them, and then whichever we, like in the exec committee, thinks is the best, we will pick one and give them the $50 PB Tech voucher. It is a group event if you want it to be, so you can work together in groups. I think the light is a bit going on and off, but yeah, it can be a group event. So if you do want to work in a group, you can, and but we only have that one prize, so it will be shared amongst the members if that's the case. For today's tutorial, I'll be going through it mostly in Python, but you can submit it in anything you can do the data analysis on anything you're comfortable with. So if you're comfortable with Excel or R, you can use that as well. And just another thing is, if you do submit like the data analysis, I do recommend using Google Colab as the attachment, because it's just, especially if you're using Python, because it's just easier to execute and have a look at what you've done. So yeah, so just gave a couple examples for what you might want to do with the data set itself, is looking at the relationship between heart disease and the other attributes that's given in the data set, and also, or maybe just find like a pattern in one of the variables that you think is interesting. But whatever you find, it is important for you to be able to explain it. So that's why we want like a little brief explanation for what you found. So yeah, just a quick look at the data set itself. So I'm just going, so this is how you, so I'm getting the data set directly from Kaggle, and an easier way to do that is just as shown here, using this, using the JSON file that the Kaggle generates. But the only thing with Kaggle is that if you want to get the file from Kaggle, you have to have an account. So that's why I'm also going to upload the Google Drive for that. So after you upload it, you can, so you have to upload it to Google Colab, and that's why I'm doing all this. But after you've done that and extracted the data, it comes as a column separated, values. So that's just like a data format. But if you open that up on Excel, it's just like a tabled Excel file. So you don't have to worry about like changing that to like an XLSX format or whatever. But and in Python, it's really easy to read CSV data using the Pandas module by just doing this method, and it creates a data frame object which stores all the data. So if we just have a look at it, this is what it looks like. And this is just a brief description. So target is whether the patient has heart disease or not. And we'll go on to a brief explanation about what it means to be diagnosed with heart disease. And then there's all these other variables which are also listed here. And this is what it looks like. So one of the other things you can notice there is that there's no string values, so there's no words. Everything in this data set has been converted to numbers. So for example, with gender, it's 1 or 0, and you have to look at it to see whether one is male or female. But we'll go over that as well. But yeah, so that's how the data is presented. And once again, the idea that the thing we want for this week is for you guys to be able to find something interesting from this data set. And so if we just gave you this data set and then told you to go along with it, a lot of people might be confused because they might not understand what any of this means. For example, we don't know if one is a male or female, and there's a lot of other things that but a bit hard to tell otherwise. All the information for this data set is also available on the Kaggle website, but some people might not want to make a Kaggle account, and even then it's a bit of a, like, you have to dig through the notebooks and stuff. So I thought I'd just do a brief introduction to the data set itself, but I won't go into too much detail for this data set because the main goal is for you guys to be able to play around with it and find something interesting. So if we just go through each variable itself to understand what they mean, some of them are quite simple, like age is quite like easy to understand. That's the age of the each participant. So each row here is a single patient that they've collected, I think from Cleveland mainly. So this from Cleveland Hospital in America, they've collected all these patients' data, and this is each row is one of those patients. And it just says here, so if you look at the gender, 0 is female and 1 is male. So now you know that what this means. And then CP stands for chest pain, and it's divided into 4 values, 0, 1, 2, 3. And that's because there's different types of chest pain. And this is all obtained through history, through clinical history. And they've inputted that value from that history. And the rest BPS, this stands for the resting blood pressure that they also measured when the patients came in during their history. So this is all directly obtained from the patient during the history. And then they also have some values they've obtained from investigation. So this would have happened after they've taken the history. And col stands for cholesterol, serum cholesterol, and the units for that is in milligrams per deciliter. So that's just what these each of these numbers mean. The other thing is FBS stands for fasting blood sugar, and they've also done an ECG at rest, but they've grouped the ECGs in only 3 ways, which isn't that helpful. But yeah, this is just the way they've grouped it, where 1 is normal, 0 is left ventricular hypertrophy, and 2 shows some ST segment abnormality. Whether that may be elevation or depression, it it doesn't differentiate, and it could have just been a T-wave inversion. So that actually holds a lot of information that it's just being all grouped together.
Do you mind maybe explaining a little bit about what T-wave, ST elevation, and T-wave inversion might mean for? I think there might be a few second years in here.
Yeah, of course. So for those who haven't done cardiovascular yet, ST segment, well, like an ECG, I don't know if everyone's seen an ECG before, but it has like a P wave, a QRS wave, and then a T wave. But the important part is there's a segment between the QRS, so the end of the QRS wave, and the T wave. There's a segment that's called the ST segment, so that between those two points. And basically, one of the indications for a heart attack is when that's elevated, or another could be that it's depressed. And that's just indications of some cardiovascular abnormality. And it has to do with the ways that there's some ischemic changes in your heart, so that the repolarization isn't happening at the same time with everything. It's a bit, but that's just in a nutshell what it is. If you want to look into it though, you can as well. And so that's kind of why I'm leaving a lot of things just really general. It's just, if you want to explore each of these points, you can just look it up on Google. Everything's available. But I'm just going through the things that aren't really that clear for this data set. But yeah, so after, so these are all like general investigations that anyone at any hospital would really do for a heart disease, if you're suspecting heart disease. But then they've also done these 3 other specialized tests that aren't done all the time. But they might be if they are suspecting heart disease and they aren't too sure. So one is the exercise electrocardiogram, which is basically they get on a treadmill and they make you run and look at changes in their ECG and other things, other measures of heart function. Because it might be, the heart disease might be mild and only caused during exercise when your heart is working. So there's a few measures, variables that's listed from the exercise electrocardiogram. And one is labeled Thallium, but that's just the maximum heart rate that was achieved during this treadmill test. So that's just how fast the heart rate was when the person was running really hard. And then this thing called Exang, which stands for exercise-induced angina. And exercise-induced angina is basically, so angina is chest pain. And exercise-induced means that it happened during exercise. So during the treadmill run, if the patient had chest pain, then they had exercise-induced angina. And this variable called old peak, so that's if there was an ST depression during the exercise. So while they were exercising, if there was an ST depression, that means that there's a transient some abnormality, so like an abnormality that's not fixed but comes with exercise in the heart. So that means that there is some pathology there, but it's just not there all the time. So that's what old peak indicates for these patients. But of course, they might actually not have heart disease. So all of these are just indications, but they might not. These might all indicate to heart disease, but in the end, they might not have it. And that's the interesting part about this data set is they have all these measures for measuring whether someone might have heart disease, but they might not. And that's what this data set is trying to figure out, is what is a good investigation for diagnosing heart disease. And so the next variable is slope, and slope is the peak exercise ST segment. So what this means is that during peak exercise, so during their maximal exercise level, which I don't really know what they mean by that. I guess they were like, it was all time, so the treadmill was time. So I'm guessing it will like increase intensity and then decrease intensity. And then at their maximal intensity of exercise, they looked at the ST segment and looked at the slope of the ST segment. And I don't really know, we don't really talk about the slope of ST sigma too much, so I don't really know what that means. But this is just something that they recorded as well. And these are all the variables that they've made available for exercise ECG. The next investigation they did was cardiac fluoroscopy. And cardiac fluoroscopy is where they, I'm not entirely too sure about the whole process, but from my understanding, it's basically, they put something like like a dye into your blood, inject it into your blood vessels, the coronary vessels, and look at how patent they are, basically. Because if they're blocked, then it wouldn't be, the dye wouldn't go through as well. Well, even if it was like narrowed, it wouldn't go through as well. And this is what this indicates. It's the number of major vessels. I'm not too sure what major vessels means here as well. Maybe that's something that's explained in fluoroscopy procedures. But this is also recorded as an investigation result. The other thing they did was a Thallium Centigraphy. And I'm not too sure if that's really done much, but this is one of the results that they recorded as well. And that's basically where they inject radioactive isotope of thallium, I think. And they record the, so myocytes, which are heart cells, they absorb this certain radio isotope, and they will absorb it, and then, but if they're ischemic, so if the heart tissue is dead and it's been scarred, then they won't absorb it. Or if it's ischemic, I think they won't absorb it. So this is also just one of the measures of basically heart muscle damage. But once again, if you want to look further into this investigation, you can look it up on Google, and they will have a lot of information on that. And then lastly, so this is how they diagnosed whether the patient had heart disease or not. And the gold standard is basically the coronary angiogram. And so they did the coronary angiogram, and if they had vessels that had a diameter of more than 50% narrowing, so if they're major vessels, I'm guessing the major vessels is their coronary vessel arteries, and if those arteries were narrowed by more than 50%, then they were said to have heart disease. And that could be with any number of the vessels. So even if one of the vessels was stenosed to that degree, then you would say that they had heart disease. So that's a brief description. I'm sorry if I went a bit fast for that, but I have recorded this, so, and I'll try and make this available, this notebook available for you to look through it later as well. But that's basically a brief overview of each of the attributes. And just a side note is that if you do go on Kaggle, they do have a lot of other people have already done analysis on this data set. But there is still, I think there is still quite a few that hasn't really been explored, but there is a lot of notebooks out there that's on Kaggle that you can have a look to see what other people have done to give you an idea of the data set as well. So that's it for the data set, and that's really it for the Datathon procedure in a nutshell. But a lot of people who haven't really done this before might be lost and thinking like, now you have the data set and you have a small understanding of what it is, but then you still don't know like where to go from there. And so I thought I'd do a little tutorial and cover basically how you can approach a new data set and how you can look at just when you come across a data set, how you can approach it. And I think this will be really useful if any of you are ever interested in doing research, because research is all about collecting data and figuring out what to do with it. But sometimes you might just have this huge data set, but then you just don't know what to do with it. So that's just what this is just one of the ways you can approach those kind of situations.
Can we get
So
a bit of an indication of how much experience people in the group have with data analysis? Maybe just pop a comment in the chat, give us a bit of an indication as to how much you know, if you're a complete beginner, which we've sort of tailored this workshop towards, or if you have a bit of experience with data analysis, or programming in Python, etc. Just be interested to know. It would be helpful for us to pitch the tutorial at the right level. Thanks, guys.
yeah, that's good.
Looks like mostly beginners.
Yeah. Well, yeah. So hopefully this tutorial is useful then. But basically, yeah. So now what? What do all these columns mean? And I think that's that's the first thing that you should do if you don't really know how to approach a data set, is to figure out what each of these values actually mean. And we did kind of do that, although I went through it quite quickly. We covered that. So moving on then, now that, say that you have gone through all of them and then know what it is, like what each variable means, basically. And so you have that understanding, but then what? And so then what you can do is you can start this process that is called exploratory data analysis, because that's literally what it is. You're like exploring a data set. And so yeah, so I'll start from there and kind of go over a brief overview of what EDA is. So exploratory data analysis is really graphical in nature. So you want to be looking at like the relationships visually to see the structure of each data, basically. And hopefully that makes more sense later as we actually go through it. But basically some of the goals, like, so why would you ever want to do exploratory data analysis, is really because you're trying to understand the data set more. And by doing that, you can then begin to think about, is there anything interesting you found, like that could be worth exploring further? And then that could formulate a hypothesis which could lead to a research. Like, that's what research is really. It's like trying to figure out whether your hypothesis is correct or wrong. So yeah, that's what it is. But another thing you can also that's also useful about EDA is that you can figure out if the data set has actually any problems. It won't figure out all the problems, but it will help find the easy to see problems that's been made with the data set. So this just another disclaimer is that this HART data set that we have is quite clean, so it's been prepared quite well, but there are some things that are incorrect with it. And if you don't figure that out and correct it, your interpretation will be wrong if you use the wrong parts of the data set. So that's just a heads up for people who never. So that's what's important about like looking at the data set, is to figure out if there's anything wrong with it. And then after you fix that, you can then also figure out what is there anything interesting that you can maybe look deeper into. But of course, you don't actually have to do EDA to know if there might be anything interesting, because a lot of the time people think of a question first and then look for a data that matches their question. But this really is the opposite approach, where you are given a data set first, and then can you find anything interesting from it? So yeah, so that's how it is. And EDA, like I said, is very graphical. So what that means is you want to be drawing graphs and you want to be plotting things. And why is that important? Because why can't you just look at tables of like the means and the standard deviation and stuff like that? And so I thought I'd just do a little quick summary about why graphical exploration is actually very useful compared to just like data analysis using numbers and other statistical measures. So this is what's called the Anscombe's quartet. And it's a series of 4 data structures, data sets, basically. And if you just have a quick look at the data set. So this is the 4 data sets, and it's really simple data set. So it has just the X and the Y variable, and they all contain some level of integers. And what I've just done here is I've just ran this method that's attached to all these data frames that lists a statistical summary of numerical data. So this has to be numerical data, but it provides a summary. And if we just have a quick look, pretty much all 4 of these data sets seem quite similar. Like a lot of the things they have, a lot of the values are identical. And there are a little differences that you might be able to pick out if you look into it, if you look at the numbers hard enough. But it's a bit difficult to figure out what these data sets, how these data sets might actually differ. But if we then plot these 4 data sets, we can see in a minute, it's actually really clear that these 4 data sets are very different. Each of these data sets are completely different spreads and distributions of the data points, So for example, if somebody then came and then wanted to infer from this data set, so basically predict the next data point that's to come, and one of the ways you can do that is to draw basically a line of this fit. But as you can see here, except for this one, all of these are incorrect. They don't really fit the data. Like if you remove this outlier here, then this would be correct as well. But because of this outlier and this outlier, like these are just all you can't do a linear regression on them because it just doesn't predict accurately. So that's the, but you wouldn't have been able to figure that out properly without looking at it graphically first. I mean, you might have, but it's a lot difficult. And that's really the point of visual exploration of data sets, is that in an instant, you can see the structure of the underlying data. So that, however, that doesn't mean it's not important to look at the numbers too. So we'll have a quick look at how you can explore a data set. And I won't be using the heart disease one because that's for the Datathon and for you guys to have a look through. But I will be using this other data set of placement data. So we'll just have a quick look at that. And this is what it looks like. And this isn't important for you guys to know, but just a brief summary so that when we go through the other examples, it makes a bit of sense, is that this is each individual ID number of, so each row once again is one participant in this data set. And once again, there's a gender row. So this gender column. So this just shows the gender of the participant. And all of these here, what they represent is their test scores through secondary school and high school. So this is their secondary, actually so this is like, so secondary school here, you might be thinking is the same as high school, but in this, this is a data set from India, and this SSC is before high school. So think of this as junior high. So this is the average average exam percentage out of 100 that these people have received during their junior high school years. And then this is the average percentage they received during their high school years. And whatever this B means is just what sort of school they went to, whether it was a central, which I think is public, and other, which is like private or like some other school. And degree percentage, once again, means so during their university years, what their average degree score was. Degree T indicates what department they were in. And this E-test is, well, work X means work experience. E-test is what their exit test score was. Specialization is what they specialized in during their university years. and sorry, not university, is what they specialized in during their master's program. And then MBAP is their master's degree percentage. And then the final things is whether they landed a job and how much that job paid. So basically this data set, in summary, is looking at how well somebody did academically and then seeing how that relates to whether they landed a job and how well their job paid. So I thought that was an interesting data set to have a look at. And in Python, so this is how you can begin in Python if you were using Python, is you use this thing called a Pandas Library, if you've never heard of that. This is just like a module that you can import, which I did at the beginning. So I imported a series of these libraries that I'll be using later. And if you guys don't really understand much about Python, sadly, I can't go over everything about Python in this tutorial because I think I'll run out of time. But after this, during the whole week, if you go over to the NBCHP Discord server and just ask any questions there, I can answer that. And if you want to know more about how to work with Python, I can help you there as well. So yeah, so just check out the NBCHP Discord channel if you want to for that. But basically, when you have a data frame, Pandas let you do all these easy summaries. And one is the head, which shows you the first 5 rows. And another thing you can do is you have this thing called info. Oops, why is that not? I think I've just been on this for too long. Okay. Yeah, sorry about that. So yeah, so this is the data set, and then what we can do is have another look at it in a different way. And this, we looked at it before with the heart disease data set as well, but this way just lists each of the columns. So because if we have too many columns, this row won't come out. It will just keep going and it might be too big. So you can just list it out in a vertical way so that it's easier for you to look at all the attributes individually. And then this looks at non-null count. So what that means is how many data points for each of these columns there are that isn't null. And null, it means like there's a missing value there. And then lastly, it also shows the data type. And the data type is a quick way. So this is what Pandas infers from the data you've given. So it might not be correct, but it's a quick way to figure out what sort of data there is. For example, int means it's an integer number. And this is what this thing thinks it is. And it is true in a way, but this SL no is actually, it's serial number. And when you're thinking about serial number, you can think of it as an integer, but you don't really want to be doing like calculating the mean and stuff for serial numbers. So it's not actually very useful for it to be an integer. But that's just when you deal with analysis, you have that kind of problem. But otherwise, it's done a pretty good job and labeled all the percentages as floats, which are numbers that have decimal points in them. So it can be fractions and stuff. That's what a float means. And objects, which are words and like anything else. It's not really numbers. And then we can also look at a description, which once again does a summary statistics like the mean and the quartiles, interquartiles, and the standard deviation and the max and the min and the max value. But this, once again, it doesn't work for non-numerical data unless it's specifically labeled as categorical data, and we'll get to that. But these are all categorical data, but it hasn't been labeled as such. And because of that, it only takes the numerical values and does a numerical statistical summary. And we can have a quick look. And we can see that there's something weird here, that the minimum value for all of these data is -1, which doesn't make sense, right? How can a serial number be -1? And how can any of these percentages be -1? And how can a salary be -1? Like that, you can tell instantly that there's something wrong with this data set. So, and that's why these summaries are really important. It's a quick look at the data set in a concise way to see if there's anything obviously wrong with it. And we found something here that's obviously wrong. It's this -1. We don't know if that's one row, one participant. Most likely is, but obviously there's something wrong there. And another thing about that's good with this exploratory data analysis is that you can have a look. So Pandas also has this thing called duplicated, which basically returns any rows that have been duplicated. So if I run that, it just lists as false, and then basically what happens is as long as the Pandas data set has another row that's exactly identically the same as a previous row, then it marks it as true. So indeed, we found one row which is identical to another row exactly, which is probably an error, right? Like each of these rows is supposed to represent an individual. And if there's two individuals with exactly the same test scores and serial number and salary and everything, it's a bit like, you know, that shouldn't be right, unless, I don't know, we adopt doppelganger twin. But then even then, the serial number shouldn't be right. So yeah, so what you can do then is you can quickly just drop duplicates. And what that will do is Pandas will quickly just drop that one duplicate row we found. And if we do that, we can find that the sum of these, so basically, it's basically saying that there's no more duplicates in this data set. However, if we just go back and have a quick look again at the columns, and just think about how this data set might have been created, right? Each of these has a serial number, and I'm guessing that serial number is probably just generated as somebody types in a row of information for a participant. But imagine if the person who was typing the row accidentally forgot that he's already typed in one participant and then typed in another row. If he put that in, the serial number will be different, but all the other rows will be identical. And if that's the case, then it won't be picked up by this duplicated thing because the serial number is different. And so to look out for those kind of scenarios, you just have to look for duplicate in a bit more special, like a filtered way. And the way you can do that is, first of all, I make a list. So if you don't know what Python lists are, it's basically just a list of strings or numbers or whatever. And that just makes it easy for me to go through a lot of different strings and numbers. So what I've done is I just made a list of everything, all the columns except serial number. And then what I'm going to do is I'm going to look for duplicates. Look for duplicates that that match everything except the serial number. If that makes sense. Yeah. So basically, ignore the serial number and look at all the other rows. And if they all match exactly to another row, then you mark it as a duplicate. And that's what it's done. And once again, it's found one duplicate. So we know that this is probably a wrong value. And this is just all this thing that we've done so far is a process called data cleaning. And when you get data, like this data set's pretty clean, and I've just purposely put these mistakes in there. But a lot of data sets, when you first come across them, are very unclean. Like they have a lot of problems in them. And these are just a couple common problems. So you could have duplicates and just wrong values in general. And this is just a couple ways to deal with that. So once again, I'll drop it, and then we no longer have to worry about that duplicate. And then remember that we had that weird value of -1, so we don't want that as well. So we want to drop that as well. And but we just want to make sure that that one row, that -1 is caused by one row and not multiple rows. So we just look at that one row, and then we can see that this one row has all -1s. So there's clearly something wrong with this row and we don't want it. And so we drop it. And then now if we do the analysis, we can see the minimum value is a lot more, it makes a lot more sense now. And so that's just a quick summary of how to begin data cleaning. And just a heads up is that the heart disease data set. So the reason I covered data cleaning is there's a couple abnormalities in the heart disease data set that needs to be addressed. And it can be done with these methods. So just watch out for weird values that might not make sense. And the only way to know if something is weird is if it's not being mentioned in the attribute when you were looking through the attributes, if that makes any sense. So for example, if we go back to chest pain, we can see that there's 0. The chest pain can be 0, 1, 2, or 3 if we follow this guidebook. But what if there was a value of 4 in the chest pain column? Unless you understood that chest pain can only be 0, 1, 2, or 3, you wouldn't have figured out that 4 shouldn't be in that data set. And so that's one of the reasons why it's really important to first understand each column. But yeah, so we do all that, and then after that, we can actually start visualizing and looking at each variable and figuring out if there's anything interesting in the data set. So just a quick summary for people who hasn't done statistics or forgot about it, is just looking at different types of data that exist for statistics and the different way we have to approach it. So the two easiest differences is you have categorical data, which are data that's not, they're not numbers basically. So they're like colors and gender, and, or even like trying to think of like something like a rating, like a movie rating, from S to like, or like A, B, C. Something like that. That's not numerical, so that counts as categorical data. And numerical data is like height and all the other numerical, like all the other number data. And each one of those also splits as well. And but these aren't actually so when you see nominal, ordinal, interval, ratio, that's not actually a type of data type. That's a level of measurement. That's just a slight distinction. So when you talk about data type, it's really only categorical, numerical. And then within these data types, there's different levels of measurements. For example, this ratio isn't what you would normally think of a ratio where it's like 1 to 1 or 2 to 1. Ratio just means that the numerical value has a true 0. So for example, when you measure temperature in Celsius, that's an interval because the level of measurement, the 0 isn't actually the true 0 of the temperature. But then if you're using Kelvin, if you're measuring temperature in Kelvin, 0 is the absolute 0 of the temperature. So that's a ratio. That's just the level of measurement. It's not too important for basic analysis, but that's just what it is. And nominal and ordinal for categorical data just means that. So if it's nominal, it means there's no order. So for example, gender, male, female, there's no order to that. It doesn't matter whether female is 0 or 1 or male is 0 or 1. There's no meaning to those numbers if you replace male and female with those numbers. There's no difference. But if it's ordinal, then there is some order there. So once again, like movie rating, A, B, C, you can't then like label C like 2 and then A 1. It doesn't make sense because A has to come like after, if that makes any sense. Yeah. So there has to be some order in that data when you're dealing with it. So the first thing I want to do then is we have all this data columns, all this, but they're all just a mix of categorical and numerical data. And when you're exploring data sets, it's really easy to first separate categorical and numerical data because it's just easy to work with one data set and then the other data set. And then maybe you can bring them together to look at other relationships. But when you're just looking at the basic elementary stuff about the data, it's really useful to separate it into the two categories. So that's what I'm doing here. Well, and the other thing is I don't really care about serial number. That's not really important for my data analysis. So I'm just going to remove that entirely. And then let's have a look at the columns. So this is all the attributes that, all the different variables or attributes or whatever columns that we have for this data set. And we want to separate it into categorical variables. So I've just made a list here of the categorical variables. I want to filter out, so that's what this is doing. I want to filter out the data set so that it just has the categorical. And then whatever is not in this must be numerical. So that's what I've done here. So basically I've dropped all this for the other one. And then if we have a look, you can see that it's been split properly so that numerical data frame only has numerical data and categorical data frame only has categorical data. That's what it looks like. And then this is where the interesting stuff comes like this. Is like, so now that we have this, what do we do? Well, we have categorical. So categorical is generally easier and simpler to explore. Excuse me. So we'll start with that. And the simplest way to look at categorical data is to count what categories there are in that column. So for gender, is it male, female, and other, or like how is it categorized? So we want to know, because we don't know if it's just two or how many there are. So a quick way to do that in Python is using this. It's a different library now. SNS is a shorthand for Seaborn, which is a really nice library that gives pretty graphs, but also like very useful graphing techniques. And one of them is called a count plot. And what that does is it looks at one column in a data frame and counts for each category there is for that one data frame, it counts each of those categories and to give a value, a representation of what it is. And another way you can do that in a table form is listed here with this method called a value count, which is intrinsic to Pandas data frame. But that's just Python stuff. But if we have a look then, this is what we get. So this is the table. So there's 139 males and 76 females in this data set. And if we look at it graphically, it looks like this. You can see that there is a difference here right away, that there's a lot more males in this data set than females. And that's a bit, I don't know, like you might have expected that, but it's a bit, I don't know, something you can explore, I guess, because is this by chance? Is this just because the same sample happens to have more males than females by random chance? Or is there an underlying reason, like another reason that's making it so that there's more males than females? And there's a really easy statistical way to look at that. And that's, this isn't really descriptive statistics, this is more hypothesis testing, but just a quick aside is like, from exploratory data analysis like this, we can think of something like that where, we can look at this and say, oh, is this by chance, or is this, is there some reason that this is happening? And it is quite obvious, I think, just looking at it graphically, the degree of more males than females makes it quite unlikely that this is by chance. But if you wanted to be really rigorous, you can do a quick binomial test, because this is a binomial distribution, and have a look at the p-value, so the probability that this distribution has happened by chance. And as you can see, this is if having a male and a female participant is 50-50, And this red distribution here is our sample distribution. And if our sample distribution happened by chance, then the probability is like 0.02%. So that's quite unlikely. So there is probably some underlying reason why there's more males than females in this data set. And we don't really know what that is, but we now know that that it's not by chance. And in this, it's quite obvious, but there are, in some other cases, it might not be. And that's why you do this kind of thing to figure out if it's actually, if that difference is real or not. But say then we have this gender, and then now we want to look at, we want to compare this gender variable to some other variables. And we're keeping with categorical data here. So now we're just going to be looking at status. And if you remember what status was previously, status is whether they got a job or not. So I've done a quick count plot again to look at the count of females who got a job, didn't get a job, and males who got a job and didn't get a job. Now, with this graph, you might be thinking, well, there might be a few things you can think about this graph. But the first thing you really need to think about is this comparable? Like, how do you look at this, and how can you compare between these values and these values? Because we know that there's twice as more males than females. So it's a bit hard looking at this to compare. And so that's why when you're comparing, it's quite important to standardize your variables, because otherwise comparisons can be quite biased. Like from here, it might look like, a lot more males got placed than females. But how real is that? And it also looks like that more males didn't get placed compared to females. So the thing we want to do then is we want to standardize that to see if that is actually real. Basically, what I'm trying to say is you don't want, when you compare between two categorical variables, don't just compare it like the raw values, because that's difficult to interpret. You should standardize your values first. And the way to standardize this is really simple. You just turn it into percentages. So what that means is what's the percentage of people in the male group that got a job, and what's the percentage of people that didn't get a job, etc. So if we just do that, so this is another table representation of the exact same thing here, but once again we want it to be standardized to be, and that's what I've done here. What I've done here is I've created a quick calculation of the percentages of these values. And I did that using these table values. So that's what's important. That's why it's good to also have the tables, because if you want to do some quick calculations, it's easy if you have the actual numbers rather than the graph. And you don't have to estimate from this. Yeah. So I've done it here, and we can see from this, this is a much more realistic comparison between these two groups. And we can see the not placed is reversed in this case, and that's a bit odd, but it might not mean anything as well. But that's why it's important to standardize things, because otherwise you get the wrong interpretation. But it is true that there is clearly a difference between females and males placed. And yeah, and just on a quick aside, which I thought might be interesting, is another. So basically, we figured this out, and we want to know then, is this effect real? Like, is there a real? So is it more likely for males to get a job than females? And that's an interesting question that you can explore, and something that looks to be true from this data that we have. But we don't know, once again, if that's by chance or not. And you can do a quick statistical test to basically look at whether that is significantly different. And for categorical values, I don't know if people have done statistics here, but for categorical variables, there are 3 tests, but we're only going to look at 2 here very quickly that people use. to match them. And one's called the Phish's exact test, and that only works if you're comparing categorical variables that have two categories in each group. So like this, so there's two genders here and two whether they've been placed or not placed. So if that's the case, you can do a Phish's exact test to see whether the difference here, the groups here are different. And then there's another one called the chi-square test. I don't know if you've heard that in biology, but yeah, that's another statistical test to see whether this distribution is by chance or not. And that's just a quick summary. But I won't go too deep into that because it's not the main topic. But I just thought so I show you like what more you can do when you figure out these interesting things. But yeah, so that's what it is. And another thing you can do because like I don't know if you've done pop health, you know like there's odds ratio and all that, guys. And you can do that exact same thing with categorical data. You can look at the odds of people getting in and not getting in for the different genders. And that's just a quick thing I've done here is I've looked at the odds ratio. And if I plot the odds ratio, so you might have seen this in a couple of like papers, if you've read a paper or looked at the results. They have a lot of these odds ratio with a confidence interval. And basically, you can do that exact same thing with any sort of categorical data that you come across. It's quite, yeah, and it's just a simple representation, simple and nice representation of whether what you found, if there is a real difference between two categorical variables or not, or if there's a real relationship between them. And an easy way to know that is if this confidence interval crosses 1 or not. And this has crossed 1, so this isn't statistically significant. So you can't say with confidence, you can't reject the null hypothesis, which basically means you can't say for confidence that this effect is real, that there is more male than female. But it is tending towards the higher side, so that might just be because we're lacking enough statistical power, so we might not have enough sample size to see the real effect if there is one. But from what we have, we can't say that this is real. So this is probably just by chance. That's all you can say. And so moving on to numerical data. Sorry if I'm just going through this all really quickly. Please ask questions along any of this or anything you want me to cover that I just whizzed over, because I can go over and cover it. Yeah, if you guys want me to. And so I'm just going to move on to numerical data as well now. So with numerical data, the easiest way to visualize. So what, sorry, so I forgot to explain the purpose of this is really what ways of visualization you can use for what data. So for categorical data, the best way to look at categorical data, in my opinion, is a bar plot. And that's what a count plot is. It's a bar plot of the count. And that's the best way, I think. And the best way to look at comparisons is you can do a distribution of the probabilities of these variables if you want. But the easiest way is looking at a standardized comparing bar plot. So I think that's the two most effective ways to visualize categorical data. Never use pie charts, I think, because that's, I don't know why it's still a thing. Yeah, just, I don't know, it's stupid. And then with odds ratio, you can do this confidence interval and represent it like this, which I think, once again, is a very nice representation. Very easy to see if there's an effect, if there's a relationship between data or not. So yeah, so moving on to numerical data then. Numerical data can be a bit more complicated, but it's not that much more complicated. And the best way, I think, to look at the spread of numerical data is through a histogram. And a histogram, if you remember from like high school and middle school math, is a plot with where you get numerical data, but you plot it like a bar plot. But because numerical data, you can't have discrete values, you just bin them. So you get the range from 0 to 5. Then any numerical value that's within 0 to 5 you count that. And that's what a histogram is in a nutshell. So this is a histogram, and I looked at the degree percentage. So this is the average exam percentage that each student got in this university. So if we look at it, we can see that we have 215 data points. So 215 individuals who we have of their average degree percentage. And then so this degree percentage is the average exam mark they got over the course of their degree. So if we look at the average of that, we can see it's 66%, which it's interesting. It means that on average, people pass, right? That's a good sign. And we can also look at the variance of their data. But once again, like looking at this is a bit difficult. So the simplest way to look at that distribution is through a histogram. And this shows a somewhat nice distribution of the data. I don't know if you guys have heard of it before, but things like test scores, it's usually a normal distribution because it's on average, people do bad and people do good, but on average, everyone does like similarly. So on average, your test scores are normally distributed. And a lot of things in the world are normally distributed. And that might not mean much at the beginning, but once you're getting into like the inferential statistics that I did a little bit before, like calculating the odds ratio, calculating the chi-square test, stuff like that, and looking at maybe doing a logistic regression, things like that, it's really important to understand the distribution and what the distribution of the data set is. Because if, for example, if you want to do a logistic regression on a data set that's not normally distributed, it doesn't make sense. You can't just you can't do that because it just gives a wrong result. And so that's why looking at distributions is interesting. But that's not the only reason, because things in nature by chance is normally distributed. So if it's not normally distributed, it means there's some underlying structure that's pushing it to be not normally distributed. So that's also an interesting thing to look at. So just a few ways to visualize this, like a histogram. But then a histogram like this, you can't really tell if this is normally distributed, right? Because the data isn't, it's not very, like we don't have enough samples basically to represent if this is normally distributed or not. Well, we don't even know if this is normally distributed. So one thing you can do is you can make the bin sizes smaller. So the gaps between the width of each of these bars, you can make them smaller. That might give a more accurate result. But a nice thing you can do on Python or any other visualizing tool you can use is this thing called a KDE. So a KDE is a kernel density estimator. So basically what it does is it creates a standardized approximation curve of the data set that you have. And so if I show that, oops, that's not the right one. I don't know where it is. Oh yeah, so this is what it looks like. So this is the KDE, this blue line here is the KDE plot. And you don't have to think too much about that, but basically that just shows the trend line. You can think about it that way, the distribution trend line of this histogram. So I put the histogram there for you to see and compare. So this histogram is the exact same thing as here, except it's been standardized on the x-axis. So then if you look at this blue line, and I've also laid over this black line here, that's the normal distribution. You can see it's very similar. Slightly different, but that's probably because we don't have enough sample size, right? But I think I would say that this test score distribution is quite normally distributed. I'll be quite confident with that. And this graph here, I just put that there because when you look at when you come across data analysis, you might see this representation a lot, and you might have also seen this in like Biosci 106. You remember from those days, but this is what you call a cumulative density function or a plot, and that basically is similar to this, but it's been graph cumulatively so that it adds up to 100%. The distribution, the probability of this distribution. That's a really poor explanation, but basically it's not too important, but it's another way of visualizing a distribution, and this is important for like more like specialized or advanced cases, but KDEs are a lot more visually easy to see, and yeah, so I think sticking with histograms and KDEs for now is better, but just wanted to point out that this is also another thing. But if you look at it here, you can see as well, so the normal, so that's the normal distribution, and that's the sample distribution, and it's very close, so we can see that it's yeah, very close. But you might also not be able to, you might want to have a really rigorous idea about if this is actually normally distributed or not. And another way you can do that is a probability plot, which straightens this out basically. That's the easiest way to think about it. It straightens it out. And this is good because people have some trouble like looking at curved lines and seeing if they fit properly, because you can't, like, this looks to be fitting, but then you don't know exactly how well it fits. So you just stretch it out into a straight line, and then you can see instantly if it fits the straight line, it's probably normally distributed. So here it looks to be very much normally distributed until it goes out to the edges. That's probably because we don't have much sample data on the edges. So yeah, so that's what this is. So this is just another way of representing distributions. But this is what I would stick to for beginning data analysis. So on that, I just want to do a very quick side on variance and standard deviations. So because this variance standard deviation is very important, but I feel like a lot of people don't have a hard time understanding it sometimes. So variance is basically, very, very simply, variance is the average distance of every point from the mean. Yeah. So that's another way of, that's a very simple way of looking at the spread of data. And it's squared because we don't want to deal with negative negative spreads like interacting with the positive spreads, because they're both going away from the mean, but we don't want to deal with that. But another thing is why do we not use absolute then? It's a common question that a lot of people might ask. But that's because well, there's a couple reasons. One is that squared is much easier to use mathematically. Another thing is that when you square something, and you look at the relationship of like n squared, for example, as it goes to the extremes, it's a larger number as it's more extreme. And that's really important when looking at variance, because when you have one point that's really far away from the mean, you want that to matter more than the ones closer to the mean. So that's just what variance is. And then what's standard deviation, and why do people use standard deviation and not use variance? Because and the reason for that is because it's standardized. Variance is not standardized. It's very arbitrary. Like when you have a variance value, it has no unit because you've squared whatever you were measuring. So if you were measuring centimeters, the variance would be centimeters squared, which doesn't mean anything really when you think about it. So you just square root it, and then it comes back down to becoming a centimeter. And that's a unit that you can understand in relation to the data set you have. So yeah, so that's just a quick aside to difference between variance and standard deviation, and they're just measures of spread, and that's really important when looking at data. Yeah, so then let's look at one more example of spread and structure distribution of a data. So this is another numerical data set, and this is a salary. So this is so for everyone who did get a job, did manage to land a job in this Indian university, they also got their salaries for that job they were offered, and then we plotted, and so I plotted that salary once again as a histogram, and laid over, I put the normal distribution and the KDE, which shows a smoothed out, better representation of the distribution. And what I've also done is I've put two lines here for the mean and the median, just to get a better representation of what's going on. So this is how you look at structure of a data set. And if you look at this data set here, it's not normal. You can clearly see this is not normal. Like this is the normal, and this sample distribution here does not fit this normal distribution. So clearly this data set is not normal. And that's when things, I think, can get interesting, because then you have to think about, why is it not normal? Why is salary more, how you describe this? You say this is peaked. So why does salary have a huge peak here that's less than the mean? There's a peak that's less than the mean. And it's very, this is what you, so it's shifted from the normal distribution, it's shifted to the left. And that's when you say you have a positive skew or a right skew. And so that's just a couple ways to describe data, describe distributions. But this is interesting. And also, there's a peak here, but there seems to be a peak down here. And what does that mean? Is that because we don't have enough data? Or there's another like peak here, peak, well, we can't really say that's a peak, but there seems to be something going on in these points. And we don't know if these are all outliers. This doesn't seem like an outlier. A true outlier, so just a point on outliers. When people say outliers, a true outlier is if it's wrong data. If the data is not supposed to be there, but it's there by mistake. But if this salary is truly the salary that someone is getting, it's not really an outlier per se. It's just an extreme value that happened by chance. But and you can remove it and you can treat it as an outlier, but it's not a true outlier. And so when you take that outlier out, you're not being able to account for that in the real population, if that makes sense. But yeah, so this is just like a more complex distribution, and you can figure out why it might be like this and not a normal distribution. And this is all purely hypothetical, but I think that the reason there's this huge peak less than the mean is because everyone wants to give, or all the companies want to give people less salary than the average. So all the companies, when they hire, they want to get people as cheap as they can, basically. So because of that, they want to give salaries that are less than the average, and so there's a peak that's less than the average. And I think that's a possible explanation, and that's purely speculation. And so yeah, so that's kind of the things you can start to explore with distributions. And another way, so this is a histogram, but with numerical data, there's another way you can look at it, and that's a box and whiskers or a box plot. And you might have seen this sort of graph as well. But this is just another way of looking at data. And this shows I think histograms show a better distribution, but this also shows a distribution. But I think the true effectiveness of box plots are two things. One is that it shows clearly the outliers and the number of outliers there are compared to a box plot, because a box plot is it's binning thing, so it might not be as obvious. But this is very clear where the outliers are. And another thing about box plots is that they're very useful when you want to compare two numerical variables. So here, I've just split salary into gender once again, because I don't know, we keep using gender, so I'm just going to keep using gender. So we split the salary of these people who landed a job into gender. And so here we can see that the average of the median, so this is the median, sorry. You can look at it here. So the black bar is the median, and then it intersects with this, so you know that's the median. So box plots show the median, not the mean, which might confuse people. But so this shows that the median is more, males have a greater median salary than females. But this is, once again, it's very much overlapping. And you can clearly tell that because it's very much overlapping, it's probably not significant. It's probably just by chance. But it is quite interesting because, and also this might change if you remove these huge outliers here. Well, the median won't change too much because that's the good thing about a median, is that it doesn't change with extreme outliers. But But yeah, these outliers are interfering with us looking at this data. But this gives a good representation of the spread. So we can see that the spread of the data is quite, like the male one is quite even, as but the female one seems to be not even, not as much even as the male one. So that's interesting, because if we come back to this peak here seems to be from this box plot, mostly in the female population compared to the male population. So that's quite interesting. So why is it that females have this sort of distribution compared to the males? And so that's something you can explore as well. And that's something that you can find only if you're looking at it like this. So yeah, so moving on then we can, there's another way you can look at numerical data, comparing, and that's called a point plot. And this is when you want to focus on the mean. So you want to compare the means and look really, is there a difference? So of the average values. So when you would do this is, if you think the average male salary really is higher than the female salary, then you can do this kind of plot. And this is the mean average salary, and this is the mean female salary, the female person salary. And you can see the confidence, this is the confidence interval of this mean. And you can see that it's overlapping, so it's clearly not statistically significant. But once again, there seems to be a tendency for males to be getting higher pay than females from this data set. And yeah, so and another way of compare, so this is looking at a numerical variable and categorical variable, and how we can compare categorical variables for numerical variables. Yeah, but say we want to look at numerical variables and numerical variables, then a scatter plot is, I think, one of the best ways to look at it. This isn't a very good example because there's clearly like very, very little pattern here. There's no pattern here at all. But yeah, so this is a way to look at numerical and numerical variables. But say like I have all these numerical columns, right? I have all this like numerical data, and then and we were doing all this individually. We picked like I picked gender specifically and then looked at it, and I picked salary specifically and looked at it. But if we say we had 100 columns, like then how do we deal with all this? Like we can't like be looking at each of them individually. They'll take forever. I mean, you could think about it and think like, oh, I think these are the most interesting to look at. But I think even then, like you might have like too much columns to look at. So one way you can do a quick look at each of these data is if you're using Python, a quick way to do that is what you can use this thing called a pair plot. And what this will do is for any numerical data, it will do a scatter plot and also do a distribution plot for that numerical data. And with this, rather than doing all this scatter plot individually, we can quickly see the different trends, or if the different relationships between each variable. So this is looking at the distributive relationships for each variable. And this is the distribution of each of the data. So we can see this one. So this is the exit test percentage. This seems to be not normal as well. This doesn't seem to be normal. Like there doesn't seem to be that many normally distributed things. And if you look at the relationships, there doesn't seem to be any like really meaningful relationship. Like there seems to be a slight positive relationships here, positive linear relationships, but like it's not very strong. The spread of the data is very, very wide for these data sets. But yeah, there is some meaningful relationships in these. And this is an example of a very strong linear relationship. But you will almost never see this in a data set. This is what you'll most likely see. And this also has like a linear relationship here, because you can clearly see that the data points are more sparse out here than here. But this is more likely a more realistic thing. And this here is an example of a completely zero relationship. there's zero relationship here between the salary and the degree, the master's average mark of their master. So that's just an example of looking at numerical data quickly and looking at a quick relationship. But you might think and look at this and say, like, for example, you might look at this thing here and say, is there a relationship there? Like, what am I looking at here? Like, this is too fuzzy for me to tell if there's actual relationship. So then what you can do is you can then do a heat map. And this is another type of graph it does a very similar thing here, but instead of instead of drawing the distributions of the things, it just gives you a number that shows you the correlation. So how correlated they are, the data points to each other. So that's just another quick way to look at things that if they're too fuzzy, you can have a look here to see if they're really distributed. And this can also help you pick out if there's anything that is like quite related to each other. Yeah, so this is a way, and it's also visual. If you can tell the colors, it's very visual. But I like to use I like to actually see the numbers. But also with pair plots, a very good thing is that with pair plots, you can actually separate the pair plot with an interesting variable that you might think is good to separate them with, like a category that you think is interesting to separate them. So I'm doing another pair plot and separating it with the status. The status is, once again, whether they landed a job or not. So I'm just going to look at, and what I really want to look at is there a difference? Is there some sort of relationship between whether they landed a job or not and any of these other numerical variables? So if we're looking at, for example, here, there seems to be some clustering. So for people who didn't get a job, they seem to be down here, while people who did get a job seems to be up here, which is quite reassuring. It means, well, I don't know if it's reassuring, but it means that people who got higher scores tend to get a job, while people who didn't get higher scores tend to not get a job. And that is quite, like, it means that your academic score has some meaning. So I think that's quite good. But then come down here and look at the salary. So the salary doesn't actually have a not placed because it doesn't, like, you can't have a salary if you're not placed. Yeah. So sorry, not looking at salary. Let's look at something like this here. This seems to me there is almost no relationship. So if we're looking at the exit test percentage and the master's percentage, so this is how well they did on their final year of their undergraduate degree, and this is their master's. It seems to be very little relationship between doing a master's and getting a job, and not doing a master's and getting a job. But what that really means is, like, do you really need to do a master's to land a job? It doesn't seem to be a much difference. That's something interesting you can figure out just by looking at this, the distributions of different plots. And yeah, so that's a few visualization techniques I think is really helpful to try out on all the data, on all the different variables of a data set to look at and figure out if there's anything interesting. And the hot data set does have, I think, quite a few interesting things. So hopefully you guys can find one and just maybe. So what I really want is an explanation. By explanation, I mean, like, I want to know if you guys can maybe give a explanation for why something might be the case. For example, I talked about the salary. It will be interesting if you guys find something like this in the hot data set. Can you give an explanation, or can you try to figure out why it might not be normally distributed, or why it might be the case? Or if it is normally distributed, is that weird? Like, is it weird for something to be normally distributed and it shouldn't be? And why is it the case? So yeah, I think that's quite an interesting task for you to go through. But for people who might be wondering, like, what can you do after we do all this? So say that you figured it out. Well, say that you did find something interesting like this, and say that now you want to know how can I actually explore that even further and like actually try to figure out what's going on here. So I talked about before, like what can I actually do with this? And I guess that depends on what you really want to do. Like, for example, do you want to be able to predict the salary that somebody's going to earn? Is that possible? And the only way you can figure that out is starting with EDA, but then continuing on with other things like like the couple things we did over there with the chi-square test and the binomial tests. You can do all these other things like regressions. You can do a neural network for predicting if it's possible to predict. Or you can do classification trees to try and predict as well. We can do ANOVA, which is another different technique to look at spreads of data. But there's all these other than statistical techniques that you can use to further explore your hypothesis. But EDA is the very starting point when you have a data set without any idea about what it is, to try and figure out, is there anything interesting that you can look at? And there almost certainly is. For every data set, if they're big enough, there will always be something interesting, something you can explore. And that's really how you progress to a hypothesis and research. So yeah, so that's all I had for this tutorial. Sorry, it became like a lecture. I didn't really have anything practical to share because it wasn't really a Python tutorial. So yeah, and this is really, it was more conceptual and more like what graphs you can use and try to visualize all those data sets. But, yeah, so yeah.
So yeah, like most of the things that you covered, I imagine you can do those sorts of things in Excel or other statistical softwares if you're more familiar with those. So don't feel like you have to use Python if you're more used to using Excel and you just want to put together a few graphs in Excel and you think that's a bit of an easier way for you to do it and write up your page. Go ahead, because you can go through, clean the data, do scatter plots. You can do all that in Excel if you're more comfortable with that. So you don't, if you're a bit overwhelmed by all the Python code that we've just gone through.
Yeah. So definitely, don't focus too much on the Python code for this tutorial. You can. So I did try to use a variety of different methods for plotting and data manipulation here, so that when I upload this, when I share this Colab book, if you do want to try this, you can really easily just copy paste what I've written here and modify it a little bit for the hard data set, and it'll work as well. So if you do want to use Python, you can just use this Colab notebook as a guide, and it should help reasonably well. But yeah, if you're more comfortable with like Excel, you can do everything I've done here pretty much on Excel. It probably like the pair plot, I don't know if Excel has something like this, probably doesn't. But like all the other basic analysis I've done is possible to do on Excel, like SPSS and R. There's all these other statistical software that you can use for analysis. If you have come across it, you can as well. Yeah, and if anyone has any questions, they can just leave a comment. But otherwise, like I said, you can always ask on the Discord server later on. And yeah, hopefully somebody submits a submission and goes into winning the $50 PV Tech prize. If only one person submits, then that person will be the one to get it. So yeah, so any effort counts. But
yeah. So don't feel like you have to put together a work of art. If you're just a beginner, this is just a good chance for you to get into learning how to basically analyze a data set. But yeah, we're giving you quite a bit of freedom with the prompt. So like if you're into machine learning and you want to run a neural network on the data, try to do some classification task, go ahead. And yeah, maybe we'll be interested.
Yeah, and I just wanted to mention as well, for the people who do want to do like more than just simple EDA and do like inferential statistics and classifications, and so on. The way I will really be looking at these submissions isn't really like how fancy or how advanced whatever they've done is. It's more really, can they explain what they found, and can they make it interesting? It's really the point. Like using, you could use all sorts of regression on all these data points, but what's the point? Like what's interesting about that? Like you're basically just like throwing stuff at the wall and hoping it sticks. So yeah, so I think what's more interesting is if you can explain what's going on, or try to give an explanation for what's going on, and try to give an explanation for why you want to use a tool. So if you're using a logistic regression, you can. But why are you using that? Like, is there a hypothesis that you think is quite interesting that you want to test out? If it is and you do use it, then sure, yeah, go ahead. But you know, like you shouldn't just be doing logistic regressions on everything, because like by chance you'll find something interesting, like something significant, but that's just by chance. So yeah, so always guide further things, but with hypothesis. Yeah. Yeah, and so thank you guys for coming. And just a quick disclaimer is like, this is all I'm not like a qualified professional or anything like that, so it's a learning process for me as well. But hopefully you guys got something out of it. I have recorded this, so I'll try to get that uploaded somewhere, so that people can look at it as well. And I'll upload this Colab book, and I'll also upload the data set as well. So thank you guys for coming. And if there's no other questions, I think that's it.
Yeah, good luck,
Thank you.
guys.